All right, so I'm just gonna quote what we were discussing last time, and we will take it from here. So we will discuss today. We will mostly discuss wave equations, and I was thinking of discussing. I was thinking of discussing care, yes, because that's where I mostly worked. So the care black holes, but today we will just keep it. Maybe if I have time, I can say a little bit of that, but mostly regarding Schwarzschild. Okay, I'm gonna mess up here. Yeah. So we will discuss mostly Schwarzschild, and that will help a lot of the calculations, even though they will still be complicated. But I will try to simplify it as much as I can. So we were looking at this toy model, which I said it was a toy model for spin 2 perturbation in GR plus some nonlinear terms equals 16 pi g whatever. And the truth is that actually it doesn't matter if we look at the spin 2 perturbations or the spin 0 perturbations. In the end, they all look like scalars. Okay, the only difference is that when you talk about these guys, the scalars have some notion of helicity, and they can be obtained from the curvature tensor. So in the end of the day, these are called the Newman-Penrose. I mean, if you really want to know about this, it's called the Newman-Penrose reduction. And at the end of the day, we just decompose the full tower into 5 scalars for the metric, and we just analyze the scalar equation. Okay, so just to write it a little more explicitly, as I wrote it yesterday. Okay, just to even be explicit what we're talking about, it's something like this. And then what I said is that we will assume some spherical symmetry and look at, and it can also simplify to know a little bit of the equation beforehand. And in particular, we know that there are Coulomb modes that will decay as 1 over r. This actually depends on the spin, but we will look at just the scalar case. So if we know there are modes that decay as 1 over r, it's convenient to have 1 over r here. And then we will have some spherical harmonics. We consider a single mode in the frequency space. Right, so this is a function of r, t, theta phi. Okay, so we want to understand what the wave equation looks like for this mode. Okay, and so the wave equation looks like this, which is deceivingly simple. And we will discuss why it's deceivingly simple. And so there is a potential. The potential vanishes at the horizon. And then there is a centrifugal barrier that you're familiar with from classical mechanics. But there is a correction close to the singularity. Okay, so all of this acts on phi L, phi Lm. So does anyone, so I mean, I started with phi Lm, but here I'm going to write only phi L. Do you know why I can ignore the M component? Right, okay, so that's good. I'm going to ignore the L component. So actually, yes, let me just write it like this. I'm sorry if you started writing with the M's. This is more general for cases where we will see that M will become important in a second because we will add a source. But for now, you can forget about the M, and then this is 0. Okay, so I want to discuss this equation first before jumping into the source situation, where we will do no source for now. Okay. Okay. So I told you guys there is an R star here, and I think that's kind of the sort of tricky, maybe not so tricky, but sort of the interesting part of the equation. Log R minus 2m. So in this R star variable, we have we were discussing boundary conditions, right? So we were discussing what will happen close to the horizon and what will happen at null infinity, right? And so we said, well, this is a black hole, not a white hole. So at the horizon, which corresponds to R star going to minus infinity, what do you think should happen? So you look at the wave equation. So what happens with this wave equation at the horizon? So you can raise your hand. Sorry. Yes. Maybe you can give the microphone. I cannot.
The third term will directly go to 0, right? So
right. Right. This term is 0, right?
Yeah.
So what does it mean? We have a plane wave, right?
Yep.
Correct. So great. So this is very important. The potential vanishes at the horizon. We don't feel the gravitational pull. So we have at the horizon we have an incoming wave. Why is this incoming? Well, because remember I started with an I omega t here. So I just multiply that with that, and I just get something coming into the black hole. Okay? And that's cool. And now what happens at the other extreme, right? So now we're going to look at R going to. So just to be more precise, I guess this is the limit. So maybe you should write it like this. I mean, it's just that it's a limit. So what happens with this as we go to infinity, right? So we go to infinity in R star. The same happens for R. As we go to infinity, this vanishes, right? But there is a catch. It vanishes not so fast, right? It's actually decaying at infinity. It goes as 1 over R. 1 over R is decaying. Sorry, 1 over R squared. Yes. Here it vanishes exactly at the horizon. So there is a difference between these two regions. So you may say, okay, there is something coming and something outgoing. But the ratio at which they decay is different. So if you look at the equation in R, so if you look at the equation in R, not in R star, you will see that this equation actually has a singular. Sorry, let me just write this quickly. What this tells you is that there is R stars downstairs. So this equation actually has a singular point at the horizon because it becomes divergent, R star. And the fact that you can expand in a plane wave, it's a fact that we refer to as a regular singularity. Okay? And at infinity, it doesn't really have a singular point. So in terms of differential equations, we call this an irregular singularity. Okay, so this is mostly if you're interested in differential equations, but these points are different. The sort of imprint of that is the vanishing of the potential exponentially in R star at the horizon, but not at the infinity. And at the end of the day, what happens is that in R, this will have, what it really means is that in R, this will have something that we call the Coulomb, sorry, let me just write it like this. I'm just going to ignore the 2m here. So there will be some term that looks like this, which is the Coulomb tail, or sometimes called Newton tail as well. Okay, and in ODE terms, if you are into those kind of things, this is called a confluent. The fact that you have an irregular singularity, which amounts to having this Coulomb tail, it's called the confluent Hoyne equation, but I just say confluent ODE. So this is actually quite complicated differential equation. It looks simple if I write it in terms of R and R star, but once I start sort of unveiling what's under the carpet, then I find that there is a difference in the decay at infinity and at the horizon. Okay, so let's just discuss a little bit of S matrix. Maybe I will, let me just see if I should draw this. Yeah, for clarity, I'll just briefly sketch the potential, just to try to understand what's going on. Obviously, if you could solve it, if you could solve this equation, this confluent Hoyne equation, you wouldn't need to understand what I'm going to do now. But the fact that we cannot solve it analytically tells us that we need to do a little bit of more thinking. So let me just draw here omega squared, right, which is the zero of the potential. And here I'm going to put my horizon. And at infinity, so it should go like this at infinity. Okay, so you can imagine there are a couple things happening just from the classical picture. So I can have states that are coming and bouncing back, right? Those would be akin to having an incoming solution and an outgoing. Is there a question? Sorry, you are too far, sorry.
If we see that the waves are decaying near the horizon, like there's a behavior something like that, then why don't we try quasi-normal modes from the beginning? Like when we are defining phi there, can we not use quasi-normal modes?
No, so okay, so first of all, I don't want to do so I'm going to discuss this now. I don't want to do quasi-normal modes. But we will see that there are quasi-normal modes kind of inevitably. I want to do a scattering. Sorry, I should have. Yes, I want to do a scattering of Schwarzschild. Yes. Yeah, but you made a good point. So what are these quasi-normal modes, right? So we have, imagine that we have something incoming, and then we have something outgoing. So that would be a scattering situation. You may be a little familiar with what happens if you go right at the peak. That's called the ISCO trajectory. Then you bounce back. And you can also go way below the centrifugal barrier, in which case you have some absorption, right? So there will be some absorption. Or even if you go below the centrifugal barrier, you can still tunnel into it. But there are these sort of trajectories which are kind of stuck, right? We call them resonances. And in this setup, what will happen is that there will be no, there will be, just want to make sure I got the signs right, sorry. Yeah, that's right. So there will be nothing incoming, yes. Sorry, there will be nothing incoming, yes. So for these trajectories, there will be nothing incoming. This is just a picture. So they will be defined by this coefficient to vanish, which are these quasi-normal modes. But I'm not interested in this. I'm interested in the case where something comes in, then something comes out, which is a scattering, right? Obviously, there will be states that are trapped, and so that's just a different part of the spectrum. Okay, so if I define it in terms of these functions, I can see that there is part of the function that goes into the horizon. So when I throw something in, there is part of the function that goes in. And that function, we say it's transmitted. So we define a transmission coefficient. Here I'm working on the omega space, right? So I have a transmission coefficient. And then I have a reflection coefficient, which is the A out over A in. Okay, and you may have some impression that the energy is conserved, right? So we have conservation of energy in the four-dimensional theory. So there has to be some idea of what the conservation of energy is in the one-dimensional problem. And you may remember from quantum mechanics or even classical mechanics that the energy is related to the amplitude, right? So there will be a conservation of the amplitude. Okay, and the way that we normalize it in this case is by saying that T, I'm going to prove this in a second, but it's something that it's kind of intuitive first, which is T squared, the mod square of T plus the mod square of R is 1. Okay, how do you prove this? Well, you look at the differential equation there, and you see that if you are into quantum mechanics, and this was really a Schrodinger equation, you would see that the particle number is conserved. So the particle number in the Schrodinger equation, whatever, is given by this. I'm going to use R here. Okay, and you can prove, maybe this, let's just say it's a homework, to prove that this is conserved. So it doesn't depend on R. So we can evaluate it at the infinity, sorry, at the horizon, or at infinity. And so we have an inflow of particles, which essentially the amplitude of the wave is conserved as we go to the horizon, and then we bounce back. So this equation, also a homework, is equivalent just by replacing what the solutions are in both cases. You can prove that the particle number is conserved, which amounts to this conservation equation. Okay, so what does this mean? It means that there is a reflection. So the reflection is interesting because it's what we are interested in asymptotically. We just care about what comes in, what comes out. We don't know what happens in the horizon. So this is the matrix that we're going to look at, and we call it the S matrix. Okay? And it so happens, imagine for a second that there is no transmission. It so happens that this equation would tell you that the S matrix is unitary, which amounts to say it's a phase. So in the case that there is no transmission, we call the S matrix the scattering phase. It's a phase, delta, And so I define it like that because it's a phase if there's no transmission. If there's transmission, all that I have is a phase that has an imaginary part, right? So delta L is real if t is 0. That's why it's interesting. Or that's why the notation is convenient. Yeah, because we have r star r equals 1. And then, yeah. And remember, this is already in a partial wave basis, right? I'm not doing the scattering of momentum plane waves. I'm doing my spherical harmonics, right? So the sort of S matrix is not really a matrix, it's a number because I just diagonalize the angular momentum, which is a conserved quantity, so it allows me to write it as a number, as an eigenvalue. So now I have this value, and if I have a little t, then my delta L will have a little imaginary part, which is the absorption. So that allows me to define, I'm not gonna expand too much on this, but the absorptive part of the cross section is really 1 minus r squared. And then you obviously have to sum over all harmonics to compute the full absorption cross section, which is 1 minus the mod square of I to the delta L square. Again, this is a very useful formula in black hole scattering. If you want to learn more about this, the sort of standard reference is a book called Scattering of Black Holes by, I don't know if it's off or off, but I think it's just off. Black Holes by Matzner et al. This book, I think people don't like it too much. They say it has many mistakes, but it's, as in the first reading, it's really nice to understand. I think the methods have improved in the last 40 years, but it's scattering from black holes. Oh, there you go. Yes. Yeah, in the last 30 years or so, people have developed more methods, so actually the book is a bit outdated, but it encapsulates all the main ideas, including this formula here. Okay, so how do we solve this equation in reality? Okay, so it's a Schrödinger equation. I'm just going to give you a little flavor of how it is to deal with this before we jump into the source situation. We solve it by something called the matching. Okay, so I'm going to do a matching calculation. I think Ricardo also mentioned part of this in his talk. And what we're going to consider is it's a region where 2m omega, so we're going to do long wavelength scattering, where this 2m omega is very small. Okay, so that means essentially the wavelength of the wave, right? So you're thinking of this wave is large as compared to the black hole. So we can resolve the black hole by looking at kind of a multiples. Okay, so this is like the black hole is small as compared to the wavelength. I'm just going to write it because maybe it's black hole is small compared to lambda, which is 1 over omega. Or, yeah. Okay, so in this case, actually, we have an interesting zones or zone decomposition, right? So we know what happens at the horizon, and we know what happens at infinity. And then there is some region, which is, so it's a region which is, sorry, there's a region in which my R, so R here, so this is R. So R here is smaller than 1 over omega. And there's a region where R is greater than 2mr. Sorry, than 2m, right? It's far from the horizon. So we can do some kind of matching in this zone, which is R greater than right, this is the matching zone. Okay, so what we will do is we will solve the equation in this region, the far zone. Just going to make it very explicit. Far zone is going to be R, and near zone, it's going to be R. Okay, so let me see how much can I do from this. So I will just solve part of the far zone equation, then I will tell you how the near zone looks like, and then maybe I will do a little bit of the matching, just so that you can have an idea. The far zone has very interesting consequences. The first one is this Coulomb potential, Coulomb tail, and we can see that more explicitly, perhaps. Yeah, let me just do it here. Okay. Okay, so it turns out if you expand the far zone equation, you can find an approximate solution in the far zone that looks like this. And this is actually not hard to do in the basis I just gave. There's some coefficient alpha, which depends on omega, and then there's some coefficient beta that depends on omega 2. So not surprisingly, there are two solutions. Those are precisely the ones that we had from the asymptotic expansion, but this is not asymptotic. This is the whole far zone equation, okay? So it's not the boundary condition, right? Okay. That's keeping the limit term in the potential as r goes to infinity, yes. And so the expansion of this actually is a bit more precise than that. So we have e to the I omega r. We have the logarithmic term 2m omega log r. Right, that is exactly what I wrote there. And then we have, well, some constant term that depends on L, which doesn't matter at large R, but it's still there. And then we have something interesting. We have the logarithm, although it's really a phase, of gamma L plus 1 minus 2 Im omega. Okay. So we get a little more information just from solving the far zone than from doing asymptotics, obviously, because we are actually solving something. Sorry, what? Oh, okay, so I'm approximating, sorry, yes, plus, I'm literally just expanding a Bessel function at the horizon, at the infinity, and then I have a complex conjugate, which I will just not write. So this here is called the Coulomb. So now there is another Coulomb, which is called the Coulomb phase, because it's a phase. And this is the thing that if you resum all the effects in L, so if you resum in L, which I just deleted, it will give you, it's related to the 1 over R potential. Okay? So this is kind of interesting because it's the thing that yesterday was giving us problems when we tried to define the force of an object at its location, right? We have a 1 over R piece, which is divergent. So we kind of want to get rid of this Coulomb phase when we do the self-force calculation, right? Okay, so that is, and there is another way of getting this expansion, which is from the, which I don't have time to talk about, but it's called the aconal limit, also known as the geometric optics approximation. Geometric optics. But you can sort of guess it from the fact that this looks like energy and, well, I'm not sure you can guess it actually, but what you can see is that this is an exponent that's essentially the on-shell action of a particle, of a massless particle, of a geodesic. So the idea is that very far from the source, you have this. I'm just trying to give you an intuition here, so I'm just going to say there is a sort of wave package traveling in some directions, and in the geometric optic limits, we can understand this as an null geodesic. And what I'm writing here is just the on-shell action of a geodesic in the large L limit, which depends on the angular momentum, which is L, and the energy, which is omega. So that's why there is an L and there is an omega, essentially. Okay, so many things can be said about this. I should refer you to the book there, and maybe some of my papers if you want to learn more about that. Then let me just briefly mention what happens at the near horizon, sorry, at the near zone, and then we will move to the charge situation. Is there any question about this? Okay, I wasn't very precise, but I hope I just gave you a flavor of what it means to. So here, what I'm getting is I'm getting these coefficients. So yeah, so I'm getting an expansion. So so what I can say, sorry, so yeah, so what I can say is that my A in, right? My A in is given by the logarithm part, which is exponentiated. So I'm just gonna say L plus 1 is to A omega. And then there is a phase that's minus 1 to the L. And then there is some other prefactors. But that's essentially what I get from and then in the other case, I just get the complex conjugate part. Right, so it's the complex conjugate, so I'm going to have gamma gamma again. But note that they don't cancel because I'm going to complex conjugate. So when I compute my S matrix, I'm still going to have, okay, sorry. I'm still going to have the Coulomb phase, which is good because that's exactly phase. Right, so I have this square times some other prefactor. So this is exactly a phase, sometimes normalized by 2 here. Okay. And the near zone is a bit more interesting. So I'm not going to solve that part. But I'm just going to say that, well, you solve it in the near zone. There is an incoming wave, right? We normalize it by 1. We normalize it by 1. It's a transmitted wave. And then we expand it. We expand this equation. So this is at r very, very close to the horizon. But what we have to do then is to take this and expand it, expand as r is very far from the horizon, right? Right. So we take this equation and then we expand it, and then what you should find, or if you open the book, is something that looks like a multiple expansion. So there is a term that looks like r to the L, and there is a term that looks like r to the minus L minus 1. Does anybody know why I have these two terms, especially these two powers? Right, so the solution has some kind of reflection, right? Yes, and that's, oh my God, I deleted it. But it's just the potential has this L plus 1, right? So you can just change and get the same potential. If you change L to L minus L minus 1, it's called the shadow transform, just changing L to minus L minus 1. So there are two terms. And these two terms, surprisingly, can be matched to the two terms of the far zone. Right? So now I take the far zone, and I just expand it. So expand the near zone for that, and expand the far zone for r less than omega minus 1. Okay, so then the far zone, this one I can write a bit more explicitly, gives me omega to the L plus 1. Okay, it's 2L plus 1, so factorial. Plus r minus L. Okay, sorry, I think I mistook. Yeah, sorry. Okay. I think that's correct. So what you have to do is you just have to match A and B, and then you get the full solution on the everywhere, essentially. You get the full solution everywhere. But you're interested in the scattering region. Oh, sorry, guys. I think I forgot. Okay. There is an alpha and beta here. Sorry. Yes. So alpha and beta are actually what matches to AL and BL. So AL and BL are known. Then alpha and beta are fixed in terms of AL and BL, and that gives the, then you can compute the ratio, which is the full amplitude. Okay. So I just want to finish with one final exercise, or maybe final point, which is the self-force calculation. It turns out the self-force actually is not that hard if you don't get into the actual solution. Conceptually, it's actually very simple, and part of it I already explained. So we have so this is self-force. Yes.
Thank you. The scalar field shouldn't like behave like 1 over r for large r in the near zone?
Yeah. Are you asking why it's not?
Yeah.
No, I normalize it. Sorry. This is, if you check your notes and you wrote the first equation, I expanded phi as 1 over r
Okay.
phi lm y lm ei omega t. Yeah. So everything is normalized.
Okay, perfect. Thank you.
Yeah, good. That is a very tricky convention that you have to be careful when books write this equation, whether they take the 1 over r off, because otherwise the equation changes and you have to, I mean, you will recover it, obviously, but there are different conventions here. Okay, so so let me just discuss a bit of the self-force calculation. So imagine, I mentioned it briefly yesterday. This is the only part that we're really going to make it very explicit that we have a black hole, right? So we have a black hole, and then we have some metric field. But the source, which is accelerating or moving in this background, has some mass m. It's going to back react, right? So it's going to sort of perturb the metric. And so what you have to do is you want to really compute this perturbation. So in this case, we're going to use a scalar toy model, which is this scalar field. This part of the equation is the same. So the scalar field is sourced by this source here. It's a J, right? So this is my scalar field phi. The part that is not the same, which is simplified by this, is how does the source accelerate, right? So I'm going to consider m very small as compared to the mass of the black hole, right? And so at first order in m, there will be a correction to the geodesic equation, which is, sorry, how to, so there's a geodesic equation, which is, sorry, I'm just going to write it. I'm just going to write it like this. So this is 0 if it's a non-accelerating particle, but there will be a term here that's proportional to m, right? And that has to do with some force. Okay, this is going to be normalized. Let me just call it u for now. This is going to be normalized. And the force is going to be proportional to some projection for a scalar field. Okay, now we're going to talk about a scalar field. It's going to be some projection on my for velocity on the gradient of the scalar field, right? So if you were in flat space and the source was static, and what this does is it removes the time components, and so you just get the usual field. I'm sorry, the chalk is not helping me here. You just get the usual Newton's law for a potential. But this potential is a covariant potential, so you need to project it in the direction transverse to the trajectory. Okay, so this is, again, I just said it, but let me just emphasize, this is a toy model, okay? What really happens is that the geodesic equation has a correction that comes from the metric, and so this will have something to do with the linearized metric, okay, the linearized perturbation, okay? But this example is good enough to talk about what happened. Okay, so we said yesterday that what we have to do in this situation, because this phi will be blowing up close to the particle, right? What we have to do is we need to regularize it. We need to take this radiative component. So how to do that? Well, we start by writing the propagator, solving this equation, and then we can take the regular part of that. So let me see. So we start by solving the equation. Right, so you have a retarded propagator. This is how you solve the equation, and then you have a source. The source has something to do with the mass, right? So let's just write the source explicitly. So the source is supported only on the word line. So it's going to be an integral over the word line times delta function on the word line. And this is a delta function in a curved space-time, so you have to divide by the volume, right? Because it's a volume form. And this is a function of x. Okay. So now, what you can do is you can put this equation in here. But first, let me just briefly discuss what the retarded propagator look like in this space. So this is a very nice calculation, I believe, due to Hadamard, which I'm not going to reproduce. I'm just going to give you the answer. But you should definitely look up this paper, which is not as well known, but it's a beautiful paper. This is by some mathematician. So we saw that in the flat space case, this was something retarded, of course. So we had x0 minus x0 minus x prime 0, if you look at x minus x prime. And then there was a delta function on the light cone, right, which we can write as x0 square minus, x0 minus x0 prime. That's the time difference, minus x, the vector, minus x prime, the vector, square delta. Okay, that's the flat space case. So how does it look like in the curve case? Well, you still have this theta function. That's just what makes it retarded, right? So that's not going to change. It's still supported on the light cone, but now the light cone is very curvy, right? So if you have your particle, you have to compute. What you have to do is you have to compute the geodesic distance, right? So let me define this variable called the geodesic distance from x to x prime, which is the it's whatever called ds, just the distance, but written in this curve coordinates of x2 minus x prime. Right, and if you want to make it more precise, you have to dx d tau, dx d tau, d tau, right? And this has to be done with the metric tensor. Okay, so this is the geodesic. This is also the action. But now what we're doing is that we are evaluating the on-shell action between x and x prime, which is the geodesic distance. Okay, so this is a function. Crucially, this is a function of x and x prime, which depends on g. Okay, so not surprisingly, what goes inside here is delta sigma. But then you have to make it covariant, right? So this has to transform as a scalar function. And you have to multiply it by a measure, which is, if I remember correctly, the mu of sigma. So this here means determinant times square root of minus gx. This is the volume at g, and this is the volume at gx prime. Okay, so it's kind of complicated, but the fact that you can even write it, and I can even show you guys, this formula is quite remarkable. And you can check that in flat space, because the volume is 1, all right, good. So this is a smooth function, which means I can expand it. I can expand it next to x goes to x prime, and it doesn't contribute to the second derivative. So at some point, I'm going to show you, well, not today, but the second derivative of this gives me x minus x prime. And you have to use the property that b is a smooth function. Okay. So is there any question regarding this formula? Yes, one question here. Oh, someone found, you found? Yeah, this is very, very old stuff from the archives of the world, not the archives of the online. Yeah, it must be, yes. The guess here is 1920, so this is like very old stuff after Schwarzschild, but way before anything else we know. Yeah, I'm surprised it's not as, do you know about it, Ricardo? Yeah, it's not as known. But it's a closed form. And I just didn't explain it, but this B actually can be written, well, perturbatively, but analytically. Anyway, what I want to say is that, OK, so what happened in the flat case? So this is also referred to tail in the self-force literature, which seems to be aware of this paper. And the story for the word line is very similar, right? So now we're looking at a point X here, and we have a source supported on the word line, right? And so what we're saying is that there is an observation point X, and there is a point on the word line X prime. And what we're looking at is the null geodesic term that goes from X to X prime. So there is a contribution from the null geodesic, only from the past. And then there is a contribution from the inside light cone, right? So there is a contribution coming even from massive geodesics, if you want, that are influencing this point. Okay? And this, so this determinant tells you how curvy, essentially how curvy these geodesics are. So for instance, you can check that the determinant is 0 at this point. So this function is 0 here, but as you go far from it, it starts going closer to 1. Okay. So we have this light cone, and we have the interior. So if we replace, now we can replace the retarded propagator inside this expression. I'm just going to call this u of x minus x prime, sorry, u of x prime. Another interesting thing is that this doesn't depend on the difference. It's a function of x and x prime. So actually I wrote it incorrectly there. Because of the reason that we don't have translation invariance. Let me just call this u. So from here you can write the form of phi. Right, so let me just write phi. I'm just going to integrate it on x. So I'm going to have a d tau. And then I'm going to have phi of x. It's going to be my propagator x at point x, and also evaluated at x of tau. And then will be some square root of g, and then the mass. Okay, I think that's correct. And now I'm going to insert this function here. Right, yeah, but I don't think I can simplify it much more if I insert it here, but I'm just going to write it explicitly. This is x tau. So this can truncate. So now I'm going to look at only the, so this goes from infinity to infinity, but I'm going to look at only the part that's in the past of x. Yeah, and x tau plus x tau. Okay. If I have more time, I would probably try to expand the actual functions u and b. But you can ask me later, and then I can tell you a little bit more, which is almost at the edge of my understanding. So I can tell you a little bit more how to expand u and b. But at the end of the day, b will be computed perturbatively. Okay, so let me just summarize what we have done and what's next. So what we did was to solve for the retarded field. And from this expression, as usual, you can check more or less explicitly that when the source comes close to the, when the observation comes close to the source, there will be a divergence. So this is just from this term, which will be evaluated this function, at sigma at neighboring points. Yeah, yeah. So all of this is the same as in Minkowski. The tail term will not contribute. So what we need to do is we need to regularize the first term. Okay, so we solve this equation, right? We solve this equation when we have the retarded propagator and the source. Okay. And now what we need to do is we need to solve for J in terms of spherical harmonics, right? So all I did there was to write it in momentum space, but we can also expand it in spherical harmonics. So when you expand in spherical harmonics, what happens is you get the same equation, which I deleted. So let me just copy it. So you get this equation. But now there will be something interesting, because I'm going to expand my source, and then my source will have all kinds of multiple modes. Well, if I consider a generic source. So let me just remind you how this JLM is defined. So you have to do an integral over the sphere, and you have to smear it with a spherical harmonic. But because we are working on in frequency space, we need to further take, so this is the S2 integral, but we also need a time integral. So this is what we have to do. But this is not hard for certain sources. Suppose we have an infalling particle. So rather than having something far from the black hole, we have something falling into it. So then when we do the angular integral, we're just going to get the phi LM back. At the location where this particle is located, let's call it phi particle, sigma theta particle. So it's going to be located at phi particle, theta particle. And then the rest is just the T omega minus T. I'm just going to write it here, sorry. Yeah, I'm just going to write this here. Okay, so the rest, so let me just copy this, phi LM, theta particle, phi particle. There's a term that goes with the mass. Then I have to do, I just did, this is doing the angular part. Now I'm going to do the time integral. Well, actually, I'm not going to do it explicitly. I'm just going to show you the expression. And then I have the f of r t. Then I have the t, the tau, which is a function of sorry, this is a function of, sorry, it's the sorry guys, 1 second. Yeah, okay, so this is RT. Okay, so the motion of the particle will be a fixed theta and fixed phi, but I'm going to have RT and T. Right, this is what I'm going to Fourier transform here. Right, I already took the angular part. Just going to have to take the time component and R minus T. Okay. Yeah, I think that's it. So this RT is fixed by the geodesic equation. And so all we have to do is to write it explicitly and then find the zero of this function so that we can take, at the end, this is going to be a Jacobian, right? We can fix T from this delta function. Okay, so suppose now I'm going to assume that we know this the calculation. So I'm going to assume that we know the function RT for the geodesic, and then we can compute this explicitly, right? Completely explicitly after we know the function RT. And so all I need to do now is to shove it into this phi LM through this expression, but I need to regularize it, right? So I need to take, so what I need to do is I need to take the retarded green function into a singular part plus a regular part, right? And the way that the regular part is defined is precisely as we saw yesterday, which is by splitting the radiative components here. So this is the radiative part. So I'm just going to tell you the upshot of that procedure. And the procedure amounts to the following. The procedure amounts to taking my phi, which is, so if you remember, we had this expansion. So we have the expansion where I take phi Lm, computed from there. And then I have the spherical harmonics. And then I have Ei omega t. So the procedure amounts to taking phi Lm computed from this expression using the retarded propagator, right? But subtracting terms that are blowing up after I sum over L. So all I need to do is I need to show you how to subtract terms that are dependent on L. So there is a term that goes like this. There's a linear term. And then there's a term that goes like L to the 0. And then there's a term that goes like 1 over L. And then there's a formula for A, B, and C given phi Lm. After you subtract this, this defines the radiative, this radiative field. Okay, so it's conceptually very simple, although I'm not going to compute A, B, and C. But this is exactly what the divergence near the source comes from. And at the end of the day, once you have this phi radiative or regular, you just plug it into your geodesic equation. So it's the mass. And then we have Okay, so now what you have is you have the source. In that case was the incoming one in falling into a black hole, but more generally we'll have some kind of orbiting solution. So it would be like an orbiting solution around the black hole. And then what happens is there is a source emitting some kind of a scalar field or the perturbation. But then there is a back reaction into the source itself, right? So that's all that we did. And so we regularize it so that here, when we accelerate the source, we just use the regular version of the field in the source itself. And I just show you how to do that a little implicitly, but conceptually, I think it's pretty clear. Yes, there's a question.
So when we are doing the calculation for the new, like with the radiative part, the U should also be modified, right? Because we have an acceleration right now.
Sorry, I heard the first part. We're doing the calculation for the radiative part.
Then we are when we are plugging it into again in the geodesic equation.
Yes.
The U should be modified, right? The U should be modified.
So the U. Oh, you mean here?
Yeah, yeah.
Oh. So okay, I wasn't super explicit, but secretly, so I'm solving this equation in the Schwarzschild background, right? So all of these U's, all of these sources are at this point just geodesics in Schwarzschild, right? And so I computed the field from that geodesic. That field is linear in the mass, right? I put it explicitly here, but I should have, I should have defined it so that it doesn't have the mass here, but what I mean is that the field itself is linear in the mass, right? And so everything else is considered at zero order in the mass. At the order that we are computing. So yes. So to answer your question, let me just be very explicit here. I'm going to put a 0, meaning this is evaluated on the geodesic. And on the geodesic, I'm going to write U0 plus U1. But U0 is inertial, so I'm just going to replace this by 1. Okay, good.
So when you're trying to calculate higher orders like U2, U3, or whatever, we have to keep modifying G and everything, right?
Yes, correct. Yeah. Then if I do the next to self-force calculation, which is the state of the art, by the way, this is as far as you can go in these ideas, because then you have to start solving geodesic equations in these curved backgrounds. 1 or 2 self-force, that's kind of it. Then you have to modify the, Great, that was a great question. Sorry, I wasn't very precise. Maybe I should wrap up there. I think that's enough. That's enough for now. I just wanted to make it explicit. All right.
Free question, just whatever come across your mind.
Yep. When we calculate U2, usually like for second order of H, the perturbation, we get log terms in them, right? And they will affect these geodesics also.
So you just to make sure, you mean the for velocity, or the
no, H. When we calculate H2, let's say.
H2.
Yeah, H2.
Okay, so now you're asking about the metric perturbation.
Yes.
Yeah. Okay, so So you're thinking my field here is a metric,
Yeah.
and then you want to expand in
Yeah.
the mass, in the self-force limit?
Yes, yes.
Okay.
Like even if we have, like, let's say, a binary system, we're calculating h, the perturbation of the metric.
Yeah. Okay.
H2 will have log terms, right? So when we plug those h in that equation where you are calculating the geodesic or higher orders of geodesic functions, my g mu nu will get modified, my u will also get modified. So I will have log dependence in my u2, u3 or whatever, right? And I do know that people also do self-force calculation with scattering amplitudes. So do we see those effects of log term in those calculations also when we use scattering amplitudes methods?
Yeah, that's very interesting. Yeah, that's a very interesting question. In principle, yes. Roughly what I'm doing here, yes, it's a bounded system, but everything is pretty generic. At some point, you have to do the actual integral over time. So that then, yes, it matters. Well, even here, when R is a bounded orbit or a scattering orbit, it matters for these modes. I think, in principle, the scattering situation is different, but I don't know if it's somehow related to the in-spiral problem. I mean, that's kind of the root of your question, right? So at this point, I didn't say this is scattering or this is it is an orbiting geodesic. All I'm doing is I'm solving for this phi using the scattering idea of calculating the propagator, the retarded propagator, which is again is controlled by the scattering amplitude. But the orbit itself is not necessarily scattering. But yeah, no, I agree. There should be some way of getting it, getting the logarithmic terms from the scattering, yeah, which are these tail terms. Yeah, I have no intuition of that. Yeah, it's a good question. Yeah.
Sorry if I missed something, but why do you have to consider M to be much smaller than the black hole mass? I didn't quite get it.
Great. So, well, because we can solve it, right? So when M is small, we know Schwarzschild exists. That's already a miracle. Okay, we don't have to have an exact solution of general relativity equation. We don't have it for a two-body problem, but for a single body, we have a miracle, which is this exact solution. And so we need to use it somehow. And so if you look at the effective one-body techniques, they will tell you, oh, these two bodies can be mapped to this Schwarzschild solution, but that's a bit too sophisticated. More kind of pedestrian is to just think of the big Schwarzschild solution somewhere here, right? So you can solve everything. You can solve the geodesic, and Hadamard solve this geodesic equation, and then try to perturb that from away from the geodesic, right? So now there will be some kind of inertial force, right? So now we have some deviation from the inertial motion, and we can compute that as a deviation from the geodesic in Schwarzschild in the mass zero, in the zero back reaction case. That doesn't mean that this case is not interesting. So the case that really uses these calculations is called the extreme mass ratio in spirals, right? Because in this case, the mass ratio, which is m over m, this one is very small, is extreme, and so we can actually use this linear term in the mass to understand the motion. And so this actually happens very, very often close to the center of galaxies, because we have a big black hole in the center of each galaxy. And so what we have is little planets and stars around surrounding the accretion, and eventually we want to understand the motion of these little orbits. This is exactly where this situation applies. The case that we are maybe more interested in this conference, in the conference next week, is the case where obviously this is not a small particle, but a big one. Right? So it's another black hole of similar mass. So then you need to start considering higher orders in this perturbation, right? So just try to get an estimation when this is coming close to 1.
Thank you.
Yeah.
Okay, so we can get to the next to last coffee break of the school, but not before thanking again, Alfredo.
All right. Thank you. And we have some discussion too.
Yes, yes. I mean, discussion and then. Wait.
One is safe, one is broke. No. I broke the one that was working.
No, you'll be okay. Just switch it off before we say something.